Welcome, friend, and thank you for being here tonight. You've arrived at a quiet corner of the universe where nothing is expected of you and nothing needs to be held on to. There's no test to pass, nothing to memorize, no goal to reach. All you need to do is rest. Let your breathing settle into a soft rhythm. Let your shoulders loosen. Allow the weight of the day to drift gently away, like dust lifting from starlight. Tonight, I'll be sharing 100 gentle facts about the Milky Way, our home galaxy, our cosmic neighborhood, told slowly, calmly, and simply to ease you towards sleep. These are soft truths, peaceful details meant to guide your mind into quieter places. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, please consider liking and subscribing to the channel. It helps others find their way here too. We'll begin right where you are, close to home, and then drift outward, through stars, through spiral arms, through the quiet halo beyond. A slow journey across the galaxy, carried on your breath. You live inside a barred spiral galaxy, a softly turning island of starlight drifting through the darkness. From the ground, you see only a pale band across the sky, but from afar, the Milky Way would look like a great glowing pinwheel with a bright bar across its center. That bar, made of densely packed ancient stars, guides the galaxy's shape, helping its spiral arms unfurl in gentle curves. Our solar system sits far from the brilliant core, in a quiet outer region where the stars are spaced wide enough for calm. Even now, as you breathe slowly, the whole galaxy rotates, carrying us along in its slow, patient turn. And as you settle deeper into this thought, your attention can drift to something just as soothing: the understanding that the Milky Way holds hundreds of billions of stars, each glowing, each breathing light into the dark. The Milky Way is filled with hundreds of billions of stars, so many that counting them would take longer than human history itself. Each star is a small sun, shining steadily across the ages, lighting distant worlds you'll never see. When you look at the night sky, the few thousand stars visible to the human eye represent only the nearest whisper of this population. Most remain hidden behind dust, distance, and the galaxy's own luminous haze. Yet they are all there, humming quietly in the background of existence. Every star adds to the galaxy's slow pulse, its gentle breathing in time with gravity. As you rest, you can imagine those billions of distant lights glowing softly, like candles scattered across a vast, unbroken plain. And from this thought, it's easy to drift toward the idea that the Milky Way itself wasn't always this enormous, because galaxies grow, evolve, and stretch over cosmic time. The Milky Way didn't simply appear in its present form. It was shaped gradually, sculpted by gravity, dark matter, and immense stretches of time. Gravity gathered gas and dust into the first clusters of stars. Dark matter, invisible and silent, formed a massive halo that held everything together, guiding the galaxy as it spun. Over billions of years, the spiraling shape emerged, arms blossoming outward, while the center condensed into a dense, bright core. The entire structure behaves like a slow-moving river of stars, flowing and reshaping itself as ages pass. Even now, the galaxy continues to evolve, gently shifting in ways too subtle for us to feel. And while these forces may seem distant, they cradle our home in an unbroken embrace. From this quiet realization, your mind can naturally drift to something more personal. The truth that no matter how wide the galaxy is, you can only see a tiny fraction of it. When you look up on a clear night, your eyes gather the light of a few thousand stars, just a thin dusting of the Milky Way's full splendor. The human eye can't pierce the dense curtains of cosmic dust that veil the deeper regions of the disk. It can't see the far side of the galaxy, or the tight clusters that cling to the center, or the vast halo stretching outward like a ghostly shell. Even the glowing band across the sky is just a cross-section of the galactic plane, not the grand spiral it truly is. This limitation isn't a flaw, it's a gentle reminder that mystery still exists overhead, waiting quietly beyond reach. And as you breathe, calm and easy, you may imagine the galaxy stretching far past that visible ribbon, a vast disk of stars spanning unimaginable distances. Thinking of those distances leads naturally to the next truth, just how wide the Milky Way really is. The Milky Way is immense, so wide that a beam of light, the fastest thing in existence, would still take around 100,000 years to cross from one side to the other. This enormous scale is difficult to imagine, but you can picture it like this. If the solar system were the size of a grain of sand, the Milky Way would stretch for miles. Yet all of this fits together with quiet symmetry, a collection of stars, dust, and space bound in a graceful rotating disk. Even though it is vast, every part moves in harmony, turning so slowly that a full rotation takes hundreds of millions of years. As you think about this enormity, let it slow your thoughts too. Let the wide sweep of the galaxy gently carry your attention toward the next idea. That much of this grand structure is hidden behind delicate drifting curtains of cosmic dust. Cosmic dust is not the kind you sweep away. It is made of tiny grains of carbon, silicate, and ice. These grains float between the stars, forming wispy clouds that absorb and scatter visible light. They create dark rivers across the sky, blocking entire regions of the Milky Way from human eyes. But behind these dusty veils lie star clusters, glowing nebulae, and brilliant newborn suns. Astronomers use infrared and radio light to peer through the darkness, revealing a galaxy far more intricate than what we see. Dust doesn't take away the beauty, it adds a sense of softness, mystery, and depth. And as you picture these drifting clouds, you may feel yourself drifting as well, gently toward the idea that this enormous galaxy was not always so full of complexity. It began as something much simpler. Long before the Milky Way had spirals or arms or a bright central bar, it existed as a loose gathering of gas and dark matter in the early universe. Over time, gravity pulled these primordial materials together, forming the first stars and clusters. As these early stars lived and died, they enriched the galaxy with heavier elements, seeding future generations of suns and planets. Slow mergers with smaller galaxies added more stars, more gas, and more motion. Eventually, the structure began to flatten into the spinning disk we know today. From this ancient, chaotic beginning arose the graceful spiral that now surrounds you, and as you imagine those early clouds taking shape, you can drift easily into the understanding that the Milky Way continues to grow even now. Though the Milky Way is more than 13 billion years old, it isn't finished. Even now, the galaxy continues to add new stars as clouds collapse in on themselves. It captures gas from intergalactic space, drawing in fresh material to fuel future starbirth. It also absorbs small satellite galaxies, pulling their stars into its halo like threads woven into a larger tapestry. These ongoing changes happen across millions of years, subtle shifts that won't disturb us but quietly reshape the galaxy's future. The Milky Way is ancient but not static. It grows like a tree, layer by layer, branch by branch. And as your thoughts settle with this image, you can drift into the realization that galaxies like ours are more unusual than you might think. Barred spiral galaxies may seem common in illustrations, but in the vastness of the universe, structures as orderly and luminous as the Milky Way are special. Many galaxies are irregular, chaotic, or distorted by collisions. Others are faint and difficult to see, containing few stars. But the Milky Way stands among the brighter and more organized examples, with sweeping arms, a structured disk, and a clearly defined core. This kind of symmetry doesn't come easily. It reflects billions of years of gentle evolution. Knowing this can make our home feel even more unique, a carefully sculpted oasis in a turbulent cosmos. And with that sense of quiet appreciation, we naturally drift toward the next thought, that even with all its beauty, the Milky Way is never truly still. At any given moment, stars are being born, stars are dying, and clouds of gas are drifting across the galactic disk. Clusters dissolve, orbits shift, and distant dwarf galaxies graze the Milky Way's halo. None of these movements happen quickly, but across millions of years, they reshape the galaxy's form. The spiral arms slowly drift. The bar in the center rotates like a glowing beam. Even dark matter is in motion, pulling softly on everything around it. And while you cannot feel these changes, they are unfolding around you right now, quiet and patient. As you settle deeper into rest, you can allow that motion to guide you to the next fact, the place you occupy within this shifting tapestry. The solar system lives in a small, unassuming feature called the Orion Spur, a minor arm tucked between two major spiral arms of the Milky Way. This spur is not as bright or densely populated as the grander regions of the galaxy, but it provides a calm and steady environment. The stars here are spaced comfortably apart, reducing the risk of disruptive supernova or gravitational disturbances. This peaceful location may be one reason life had time to form and flourish on Earth. As you imagine this quiet, cosmic neighborhood stretching around us, you can let your awareness slip toward the arms that surround it, vast glowing pathways of stars. The Orion Spur sits between the Sagittarius arm and the Perseus arm, two sweeping structures filled with clusters of young, hot stars and long lanes of drifting dust. These major arms glow brightly in infrared and radio light, but from Earth, their full shapes remain hidden by distance and perspective. Our little spur is like a side road between two glowing highways, a softer, quieter region where fewer dramatic events occur. It is a comforting place for a planet like ours to exist. And as you picture these arms stretching outward, you naturally drift toward the thought that the Sun is not stationary within them. It is orbiting the galactic center at great speed. The Sun moves in a wide, steady orbit around the galaxy, circling the center from a distance of about 26,000 light-years. This position is neither too close nor too far, close enough to feel the gravitational pull of the core, yet far enough to avoid the energetic chaos near the central black hole. Our orbit carries us through regions of varying density, sometimes passing near clusters, sometimes through calmer space. The journey is slow, taking hundreds of millions of years to complete a single loop. As you picture this gentle motion, you can allow your thoughts to drift to the way we see the galaxy from inside this orbit, as a faint, glowing band. Whenever you notice the Milky Way stretching across the night sky like a pale river, you are looking into the dense plane of the galaxy's disk. From inside, we cannot see the spiral pattern, only the overlapping layers of stars and dust that lie along the same plane as our solar system. This band appears brightest near the galactic center and fades toward the outer regions. The disk is thick with starlight, but dust softens it into a gentle haze. That soft glow is a reminder that we are part of something vast. And from this glow, your thoughts can gently drift toward the idea that we cannot ever step outside to see the Milky Way's true form from above. Because we live inside the Milky Way, we cannot float above it and look down on its spiral arms the way we do with other galaxies. The view from Earth is always from within the disk, always along the grain of its structure. Even spacecraft cannot travel far enough to capture an external portrait. Instead, astronomers reconstruct its shape from countless measurements, distances, motions, colors, and star positions. Like tracing the outline of a forest while standing among the trees, we piece together the galaxy's form through careful observation. This limitation adds a peaceful mystery to our home. And from this gentle curiosity, your awareness can drift to the motion that carries us through the galaxy. Even though you feel still, you are moving through the galaxy at roughly 230 kilometers per second, fast enough to travel from coast to coast in less than a blink. This incredible speed carries the Sun and all its planets around the galactic center. Yet everything around us moves together, so we feel none of it. Stars in our neighborhood drift alongside us like quiet companions on the same cosmic path. The galaxy's rotation is smooth and unhurried, a slow turning that spans eons. As you imagine this silent motion, you may feel your own breathing steadying, matching the calm rhythm of the stars. And from that calm place, you can drift into understanding why our region of the galaxy feels so peaceful. Compared to the bustling regions near the galactic center or within dense star clusters, the Orion Spur is gentle. Nearby stars are spaced widely, minimizing intense radiation or disruptive gravitational encounters. There are no enormous star-forming factories beside us, no violent supernova storms sweeping through. This quiet stability allows planets like Earth to orbit safely for billions of years. It is the galactic equivalent of a peaceful small town, far from the bright and busy city center. As you picture this tranquil cosmic neighborhood, your mind may soften, easing into the thought that such calmness might be essential for life to arise. Had Earth formed closer to the galactic center, the radiation from frequent supernova or the influence of the central black hole might have prevented life from ever gaining a foothold. Farther out, in the cold, sparse edges of the galaxy, there might not have been enough heavy elements to build complex chemistry. But here, in the Orion Spur, conditions strike a quiet balance, stable, gentle, and enriched. This region may be a cosmic sweet spot, allowing life to grow slowly, patiently, without interruption. As you reflect on this harmony, you can let your thoughts drift toward the idea that even this sweet spot is not fixed, because the Sun is on a slow journey through the disk. Over billions of years, the Sun has traveled through different regions of the Milky Way, encountering clouds of gas, passing near clusters, and drifting across spiral arms. Each environment brings subtle changes, slight variations in cosmic radiation, nearby starlight, or the density of interstellar gas. These shifts happen across immense timescales, gentle enough that life on Earth continues without ever noticing. It is like sailing through a vast ocean, currents changing slowly beneath you. This quiet drifting reminds us that nothing in the galaxy is truly still. And from this drifting motion, we can transition naturally to the understanding that the Sun continues its slow migration even now. The Sun does not stay in one perfect orbit. It gradually shifts inward or outward across the disk, influenced by gravitational interactions with spiral arms, gas clouds, and other stars. This migration is subtle unfolding over billions of years. Some researchers believe that this slow wandering may have helped deliver the right mix of materials to the early solar system. Others think it protected life by keeping Earth away from more dangerous regions. Whatever the reasons, the Sun moves gently through the galaxy, carrying Earth with it like a quiet passenger. From this gentle drift, your thoughts can close around something equally serene: the structure of the galaxy itself, shaped in ways more complex than a simple spiral. While many drawings show the Milky Way as a clean, swirling pinwheel, the real structure is more intricate. At its center lies a bar-shaped cluster of stars, stretching across the core like a luminous bridge. This bar influences the rotation of the entire galaxy, guiding gas inward and shaping the spiral arms that unwind from its ends. From our position far out in the disk, we cannot see this bar directly, but observations in infrared light reveal its presence. It is one of the defining features of our home. And as you think of that glowing center, you can drift into the next detail: that the bar itself helps create the bright, swollen bulge rising above the core. This bar is composed of millions of tightly packed stars, orbiting the center in elongated paths. It acts like a gravitational engine, helping organize the gas and dust of the inner galaxy. The bar rotates slowly, stirring the material around it and feeding the growth of the central region. Scientists believe it plays a major role in shaping the spiral arms, guiding them outward in graceful curves. Although we can't see it with our eyes, its influence extends across tens of thousands of light years. And from this bar, our thoughts can drift towards something even more surprising: the bulge rising above and below it, shaped like a cosmic peanut. When astronomers mapped the density of stars near the center, they discovered that the bulge doesn't form a perfect sphere. Instead, it stretches outward in a shape resembling a peanut or an hourglass, with two swollen lobes connected by a thinner waist. This unusual form likely results from the rotation and buckling of the central bar. Millions of stars orbit within this structure, creating dense layers of light. The shape is invisible from Earth, hidden behind the thick dust of the galactic plane, but infrared telescopes reveal its elegant silhouette. As you imagine this glowing hourglass, your mind can drift to the spiral arms that extend from its ends, arms that are not solid but patterned waves. The Milky Way's spiral arms are not long, fixed lines of stars. Instead, they are density waves, like slow-moving traffic patterns in space. Stars drift in and out of these arms over time, gathering more densely as they enter and spreading apart as they leave. The arms glow brightly because newborn stars form within them, lighting the surrounding clouds. Yet no single star remains locked in an arm forever. This flowing, shifting structure gives the galaxy its graceful spiral appearance. And as you imagine these patterns winding outward, you can drift naturally to the idea that some arms split, fade, or twist unexpectedly, because the galaxy is far less symmetrical than we once believed. The Milky Way's spiral arms are not perfectly smooth. Some branch into smaller segments, splitting like rivers into tributaries. Others fade into clumps or dissolve into loose stellar streams. These irregularities reveal the galaxy's turbulent history, past mergers, gravitational disturbances, and the uneven distribution of gas. From our position, these complexities are hard to see directly, but radio and infrared observations reveal the Milky Way's uneven organic flow. This subtle imbalance adds to the galaxy's character, making it feel alive and evolving rather than static. As you absorb this gentle complexity, you can let your attention soften, ready to drift into the next set of facts when you're ready. Woven throughout the Milky Way's spiral arms are long, dark lanes of dust. soft, shadowed rivers that thread through the brighter regions. These dust lanes absorb starlight, outlining the arms with delicate contrast. Though they look dark to our eyes, they shimmer in infrared light where newborn stars warm the surrounding gas. Inside these lanes, gravity gathers material into dense patches, preparing the next generation of stars. The dust softens the galaxy's appearance, adding texture and depth, like wisps of smoke drifting across a lantern's glow. As you picture these gentle ribbons winding through the spiral arms, you can let your thoughts drift to the shape of the galaxy itself, because the entire disk bends slightly, forming a soft, graceful warp. The Milky Way's disk is not perfectly flat. Instead, it bends upward on one side and downward on the other, like a quiet wave frozen in time. This warp may have been caused by interactions with satellite galaxies or by the pull of the dark matter halo. From Earth, we cannot see this shape directly, but large-scale surveys reveal the disk lifting gently into a subtle curve. This warp rotates slowly, sweeping through the galaxy over millions of years. Although enormous, it creates no disturbance. Everything moves smoothly, as if riding along a gentle swell. As you imagine this soft bending of the disk, your thoughts can drift toward another quiet asymmetry. One side of the galaxy is actually thicker than the other. The Milky Way is slightly lopsided. On one side, the disk forms a thicker layer of stars, while the opposite side tapers more thinly into space. This imbalance may be the lingering signature of past collisions, small galaxies merging into the Milky Way and stirring its shape. Even though the difference is subtle, it reveals that our galaxy is flexible, responsive, and shaped over time by its companions. As you breathe slowly, you can imagine this soft unevenness as part of the Milky Way's personality, a quiet reminder that nothing in the universe is perfectly symmetrical. From here, it's easy to drift into the understanding that many of the galaxy's hidden features can only be seen through wavelengths beyond human sight. Even though the night sky seems dark, the Milky Way glows in many forms of light that human eyes cannot detect. Radio waves pulse from cold hydrogen clouds. Infrared radiation shines from warm dust and newborn stars. High-energy X-rays flicker from neutron stars and black hole systems. These invisible colors reveal a galaxy far more dynamic than the soft haze we see overhead. When astronomers combine these wavelengths, the Milky Way appears alive with motion, streams of gas, arcs of radiation, glowing star factories hidden under dust. As you picture this unseen radiance, let it guide you toward the understanding that beneath all these layers lies the true heart of the galaxy, its stars. Using telescopes that see beyond visible light, astronomers uncover structures concealed behind dust. Radio images trace the raw hydrogen that forms the backbone of the spiral arms. Infrared views reveal warm dust, starbirth regions, and the glowing heart of the central bar. X-ray images pick out the most energetic objects, pulsars, star remnants, and the faint breath of hot gas swirling through the halo. Each wavelength tells its own story, and together they create a portrait of the Milky Way as layered, complex, and alive. As you imagine these overlapping maps, allow your thoughts to drift towards something familiar yet profound: the stars themselves, especially the quiet, long-lived red dwarfs that fill our galaxy. Most of the Milky Way's stars are not bright or blue or massive. They are small, cool red dwarfs that burn quietly for trillions of years. These tiny suns are so faint that none are visible to the naked eye, even the ones closest to Earth. Yet they dominate the galaxy, forming a silent majority that glows softly in infrared wavelengths. Each red dwarf may host planets or drifting debris, tiny systems circling a star that shines like a warm ember. Their long lifespans mean they will outlast nearly every other type of star, glowing long after the galaxy transforms into something new. As you picture these steady little lights, your awareness can drift to their opposite, the enormous blue giants that blaze intensely but briefly. Blue giants are the showpieces of the galaxy, immense, brilliant stars that shine tens of thousands of times brighter than the sun. Their fierce fusion processes burn through their fuel rapidly, granting them lifespans measured in millions, not billions, of years. They illuminate stellar nurseries, cast long shadows across dust clouds, and end their lives in spectacular supernova explosions. These stars shape their surroundings dramatically, enriching the galaxy with heavy elements. Yet for all their brilliance, they exist only as brief sparks in cosmic time, while the quieter red dwarfs endure. As you breathe deeply and visualize these contrasting lifetimes, you can drift naturally toward the idea that some stars in our galaxy are far older than even its spiral structure. Before the Milky Way developed its familiar spiral shape, before the disk flattened and the arms wound outward, ancient stars already existed. These old stars reside mostly in the halo, metal-poor survivors from the galaxy's earliest days. Their chemistry tells the story of a younger universe, one with fewer heavy elements and simpler beginnings. These elders move through wide, tilted orbits, drifting above and below the disk like wandering spirits. Their presence reminds us that the galaxy is a layered history book, each generation of stars preserving a different chapter. As you imagine these ancient suns drifting quietly through the halo, your thoughts can gently shift toward the stars that betray even more ancient origins, those with almost no metals at all. Some stars in the halo contain remarkably small amounts of heavy elements, signatures of formation soon after the Big Bang. These metal-poor stars shine faintly, often in soft red tones, and their chemical fingerprints reveal conditions that existed when the universe was young. They carry almost no iron, calcium, or heavier elements, just the primordial hydrogen and helium forged during the universe's first minutes. These stars are like cosmic fossils, preserving the memory of a time before galaxies fully formed. As you imagine their pale glow drifting above the galactic plane, your mind can naturally shift towards something more unusual. Not all stars in the Milky Way follow the main rotation. Some actually orbit backward. While most stars circle the galactic center in the same direction, some move in retrograde, opposite the flow. These stars often belong to the halo or originate from dwarf galaxies the Milky Way absorbed long ago. Their unusual motion stands out when astronomers map stellar paths, revealing the lingering echoes of ancient mergers. These retrograde stars drift through the galaxy on tilted, elongated orbits, crossing the disk at steep angles. Their movement is calm, quiet, and steady. Nothing disruptive, just different. Their presence hints at the galaxy's long, complex past. And as you picture these stars gliding gently against the current, your thoughts may drift to the way stars are sometimes born together, like families that eventually drift apart. By studying the motions of stars, how fast they move, in what direction and along which paths, astronomers reconstruct the Milky Way's history. Groups of stars moving together as if pulled by the same invisible hand often reveal evidence of past mergers or tidal interactions. These subtle patterns, invisible to human eyes, tells stories of collisions, accretion, and quiet encounters. Over billions of years, this motion smooths out, making the galaxy appear calm from a distance, even though its history is anything but. As you imagine these drifting stellar groups, you can allow your thoughts to flow toward the beginning of many stars' lives, clusters born together in gently collapsing clouds. When stars are born, they often form in groups, clusters made from the same collapsing cloud of gas and dust. These clusters can contain dozens, hundreds, or even millions of stars, all sharing similar ages and chemical signatures. For a time, they remain gravitationally bound, orbiting as one. Young clusters are vibrant, full of bright blue stars and warm dust. Older clusters, like globular spheres, are quiet and densely packed, orbiting the halo like ancient lanterns. As you imagine these clusters forming in soft, glowing clouds, you can drift gently toward the idea that most of them don't remain together forever. Although stars often begin life in clusters, many of these groups gradually dissolve. Gentle gravitational nudges from passing stars, encounters with spiral arms, and the tidal pull of the galaxy slowly peels stars away. Over time, clusters thin out, leaving behind streams of related stars scattered across the Milky Way. This drifting apart is natural and peaceful, a long, slow unwinding. As you imagine clusters gradually loosening, you can think of our own sun, which almost certainly began in a cluster too. Our sun did not ignite alone. It was almost certainly born in a cluster with hundreds or perhaps thousands of sibling stars. These siblings would have shared space with the young sun, glowing in a dense environment rich with gas and dust. Over time, gravitational interactions and tidal forces dispersed the cluster, sending each star on its own path through the galaxy. Today, those siblings are scattered across the Milky Way, distant and unrecognized, but their shared origins remain encoded in their chemistry. As you picture these long-lost siblings drifting far away, your thoughts can shift gently toward another truth. Stars can scatter and separate, but many continue drifting together in quiet clusters for billions of years. Somewhere in the Milky Way, stars born alongside the sun still shine. Each carries a chemical signature nearly identical to ours, faint fingerprints from the same ancient nebula. Astronomers search for these siblings by matching these signatures and tracking their motion across the sky. Though separated by vast distances, they remain connected by origin, quiet reminders that the sun once belonged to a family of stars. As you imagine these distant siblings glowing softly in the dark, you can allow your awareness to drift toward the quiet cradles where stars like these are born. Deep within the Milky Way, stars are born in enormous molecular clouds, vast, quiet regions filled with hydrogen gas, drifting dust, and temperatures so low they approach absolute stillness. These clouds are darker than ink in visible light, hiding everything inside them. Yet they hold the seeds of future suns. Gravity moves gently at first, pulling together small pockets of gas, allowing them to thicken, cool, and slowly collapse. Within these dense knots, energy builds as particles draw closer, forming the earliest stirrings of a star. These cloud cores settle into a rhythm, falling inward, heating up, spinning faster with time. Eventually, hidden behind swirling dust, a faint glow begins, soft, warm, and patient. It is the earliest light of a newborn star. And just as these cradles of creation hold quiet secrets, the next stage reveals how these faint glimmers gather strength and step closer to becoming true stars. The clouds that cradle newborn stars are not small or delicate. They are enormous structures, stretching hundreds of light years from end to end. Some are so large that if you could travel at the speed of light, it would still take centuries to cross them. Inside these sprawling regions, knots of gas form clusters of stars, each pocket evolving at its own pace. Some areas glow faintly in infrared light as they warm. Others remain cold, waiting patiently for gravity to take hold. These clouds drift through spiral arms shaped by nearby supernova, stellar winds, and magnetic fields. Over millions of years, they shift like slow-moving weather patterns across the galaxy. And as you imagine their size, vast, quiet, and ancient, you can let your mind drift naturally to the moment when these collapsing pockets ignite, beginning the delicate transition from cloud to star. When enough gas collects in a single region of a molecular cloud, gravity becomes the guiding force. It pulls inward from all directions, squeezing the cloud core tighter and tighter. As the gas contracts, pressure and temperature rise, creating a glowing object called a protostar. This early form is still wrapped in dust, hidden from visible light, but it shines brightly in infrared, a quiet warmth growing inside a cold, dark cradle. Gravity continues its patient work, shaping the protostar, flattening the surrounding gas into a spinning disk where future planets may form. Over time, the core becomes dense enough for nuclear fusion to begin, marking the true birth of a star. As you picture this gentle inward motion, the slow, steady gathering of light, you can drift into the next thought: how these newborn stars glow softly through the dust that tries to hide them. Although newborn stars are hidden by thick curtains of dust, they shine brightly in infrared wavelengths, revealing themselves to telescopes designed to see heat rather than light. To the human eye, these regions appear dark, but in infrared images they bloom with color, reds, golds, and soft violets, like embers glowing behind a veil. These glowing nurseries often lie within sculpted clouds, carved by the radiation and winds of young, massive stars. The dust blocks visible starlight, but infrared waves slip through, carrying the warmth of newborn suns. Observing them feels like glimpsing life through fog, soft shapes, gentle heat, quiet beginnings. As these warm regions brighten, they signal that stars are taking form deep within. And as you imagine these hidden glows, you can drift onward to the darker parts of the galaxy, places where some clouds never ignite at all. Interstellar dust, though made of microscopic grains, is surprisingly effective at blocking starlight. It forms thick bands across the Milky Way, creating dark patches in the sky that hide entire clusters of newborn stars behind them. These dust grains, made of carbon, silicates, and ice, float gently through the galaxy, gathering into dense clouds. When stars form inside these regions, their light must pass through layers of dust that scatter and absorb it. To our eyes, these places look like voids, but they are actually some of the most active nurseries in the galaxy. Only through infrared and radio telescopes can we peer through the dust to reveal what lies beneath. As you imagine these shadowed regions holding glowing secrets, you can gently drift toward the opposite possibility, clouds that never ignite, remaining dark and silent forever.
Throughout the Milky Way, countless clouds of gas drift quietly, but only some experience the right combination of density, cooling, and gravitational pull to form stars. Many clouds are too diffuse, their material too spread out to collapse. Others are warmed by nearby radiation, preventing them from cooling enough for gravity to take over. Some clouds are stabilized by magnetic fields or internal turbulence, resisting collapse for millions of years. These starless clouds wander through the galaxy like slow, drifting shadows, rich in hydrogen but untouched by the spark of fusion. They may eventually break apart, merge with other clouds, or be shaped by passing supernova. As you imagine these calm, quiet regions, you can drift gently toward the idea that even when a cloud does ignite, the galaxy's overall pace of star creation has begun to slow. Long ago, the Milky Way was much more active, producing new stars at a faster rate. Today, star formation continues, but more quietly. The gas available for creating new stars is spread thin, and much of it is warm or ionized, conditions that resist collapse. The galaxy isn't running out of raw material, but the rhythm of creation has softened, entering a more settled chapter. This slowdown is natural for mature galaxies. They shine not just with newborn stars, but with the combined light of many generations. As you imagine this gentle shift from youth to maturity, you can drift toward the next quiet truth: that even as stars die, they help spark the creation of new ones. When a massive star reaches the end of its life and explodes as a supernova, the blast sends shockwaves rippling through the surrounding space. These waves compress nearby clouds of gas, sometimes triggering the collapse that leads to new stars. The death of one star can set in motion the birth of many more. Supernova enrich the surrounding material with heavy elements, carbon, oxygen, iron, seeding the next generation of stars and planets with the ingredients needed for life. In this way, the galaxy renews itself, turning endings into beginnings. As you imagine these rippling waves moving through space, you can settle into the next thought that the Milky Way continuously recycles its own material, passing it from one generation to the next. The Milky Way is constantly reusing its own matter. Stars form from gas, shine for millions or billions of years, and eventually return much of their material to space. Red giants shed outer layers gently. Supernova scatter their elements widely. This enriched gas mixes with pristine hydrogen, forming new clouds and new stars. Each generation becomes more complex, carrying more of the elements needed for planets, chemistry, and life. The atoms in your body, carbon, calcium, iron, were forged in this long cycle of birth and destruction. As you imagine this quiet recycling, you can drift toward the next truth of the galaxy: how long stars themselves live within this endless loop. The lifespan of a star depends on its mass. Massive stars burn brightly and fiercely, living only a few million years before collapsing into supernova. Smaller, cooler stars burn slowly and steadily, shining for trillions of years, longer than the universe has existed so far. Even our Sun, a middle-sized star, will shine for billions of years before entering its final stages. Throughout their lifetimes, stars gently change in color, brightness, and temperature, following predictable paths shaped by physics and time. As you imagine these long, steady lives, you can drift into the thought of what happens when stars finally reach their ends, and how their endings shape the galaxy. When the most massive stars reach the end of their fuel, they don't fade quietly. Their cores collapse inward with tremendous force, causing the outer layers to rebound outward in a spectacular release of energy called a supernova. For a brief moment, one of these dying stars can shine brighter than an entire galaxy. The explosion sends shockwaves racing through space, stirring nearby clouds of gas and dust. These waves compress the material they pass through, sometimes setting the stage for new stars to form. The remnants of the explosion, expanding shells of gas, glow softly for thousands of years, drifting outward into the galaxy.
And within the heart of the blast, something remarkable happens. The heaviest elements in the universe are created in an instant. As you picture this sudden flare of light followed by a long, gentle fade, your thoughts may drift naturally toward the precious materials forged in that moment. Inside a massive star, nuclear fusion gradually builds heavier and heavier elements: carbon, oxygen, silicon, and eventually iron. But iron cannot release energy through fusion, so when too much accumulates, the star's core collapses. In the extreme pressures and temperatures of the supernova explosion, elements heavier than iron are forged: gold, platinum, uranium, and many others. These atoms, created in a flash, are hurled into space, mixing with gas and dust. Over millions of years, they become part of new star systems. The iron in your blood, the calcium in your bones, the gold in jewelry. Each atom was born in one of these colossal deaths. As these elements scatter across the galaxy, they enrich the material from which new stars and planets form. And as you rest with this idea, you can drift toward the quieter end of stellar evolution. The soft, glowing bubbles left behind by stars less massive than those that explode. When stars like our Sun near the end of their lives, they gently shed their outer layers. Over thousands of years, these layers drift outward, forming expanding shells of glowing gas called planetary nebulae. The name is misleading. They have nothing to do with planets, but early astronomers thought their round shapes resembled planetary disks. At the center of each nebula lies the leftover core of the star, shining hot and bright enough to illuminate the surrounding gas. The colors, soft greens, blues, and reds, come from different elements emitting light at specific wavelengths. These nebulae are brief, lasting only tens of thousands of years before fading into the interstellar medium. As you imagine these delicate bubbles expanding quietly in the darkness, you can drift toward the star's remaining core, now transformed into a dense, long-lasting ember known as a white dwarf. A white dwarf is what remains after a sun-like star sheds its outer layers. Though only about the size of Earth, it contains roughly half the mass of the Sun, packed into a dense, crystalline form. At first, white dwarfs glow intensely, but with no fusion to sustain them, they gradually cool by radiating away stored heat. This cooling process takes billions of years, far longer than the entire history of human civilization. Over time, a white dwarf becomes dimmer and dimmer until it eventually fades into darkness, becoming a hypothetical black dwarf. None exist yet. The universe is not old enough for any white dwarf to cool that far. As you imagine these quiet stellar embers fading ever so slowly, your thoughts can drift naturally to the even denser remnants created by the most massive stars. Objects where matter is squeezed into truly extraordinary states. When a massive star explodes as a supernova, its core may collapse into a neutron star, a city-sized object with more mass than the Sun. Inside a neutron star, atoms are crushed so tightly that electrons and protons merge into neutrons, forming a single, incredibly dense structure. A teaspoon of neutron star material would weigh billions of tons. Some neutron stars spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. These pulsars blink with astonishing regularity. Others remain quiet and cold, drifting silently through the galaxy. Though unimaginably dense, neutron stars are stable, unless the original star was even bigger, in which case collapse can continue into something deeper still. As you let the idea of these tiny, heavy remnants settle, your mind can drift toward the mysterious objects they sometimes become: black holes.
If the collapsing core of a dying star is massive enough, it continues to fall inward past the neutron star stage. Its gravity becomes so strong that nothing, not even light, can escape. This forms a black hole, a region where space and time curve so sharply that they create a boundary, an event horizon beyond which information cannot return. Black holes are not cosmic vacuum cleaners. They do not suck everything in. Instead, they influence their surroundings through gravity, just like any massive object. They often sit quietly unless material gets close enough to spiral inward. When that happens, the falling gas heats up and glows brightly before vanishing from view. As you imagine this deep, invisible well in space, you can drift gently toward the one black hole that affects the Milky Way more than any other, the one at its heart. At the center of the Milky Way lies a supermassive black hole called Sagittarius A star. It sits quietly inside a dense swarm of stars, dust and gas, hidden behind thick curtains of interstellar material. Although we cannot see it directly in visible light, its presence is clear. Stars near the core whip around an invisible point, some completing their orbits in just a few years. Their rapid, precise motion reveals the black hole's immense mass. It exerts a steady gravitational pull, helping anchor the inner regions of the galaxy. Unlike the violent monsters powering bright quasars, Sagittarius A star is relatively calm today, feeding only occasionally. As you imagine this massive, unseen anchor at the galaxy's center, your attention can drift to the staggering weight it carries. Sagittarius. A star is more than 4 million times the mass of the Sun, compressed into a region smaller than Mercury's orbit. This enormous concentration of matter curves space so drastically that even nearby stars race around it at huge speeds. Despite its mass, the black hole occupies only a tiny fraction of the galaxy's volume. Its influence is strongest near the core, where stars crowd tightly together. Farther out, its gravity blends with that of billions of stars and a vast halo of dark matter. Though immense, it is only one component of the galaxy's structure. As you imagine this compressed, powerful center, your awareness can drift next to the stars that dance closest to it, tracing out swift, sweeping paths. Close to Sagittarius. A star, the environment becomes intense. Stars there move far faster than those in our region, thousands of kilometers per second, racing around the black hole on tight orbits. Some complete full circuits in just over a decade. These S-stars, as astronomers call them, help reveal the true nature of the black hole at the galaxy's center. Their motion shows that the mass lies in an incredibly compact region, far too small to be anything except a black hole. For these stars, the sky must be dazzlingly crowded, filled with light from neighboring suns and glowing clouds. As you imagine these fast-moving stars swirling through the dense core, your mind can drift toward the reason we cannot see this motion directly with our own eyes: the dense curtain of dust that hides the center from view. Between us and the galactic center lies a thick veil of interstellar dust. These tiny grains, made of carbon, silicates and ice, scatter visible light so effectively that the core appears dark and mottled in optical wavelengths. To human eyes, it seems like a gap in the Milky Way's glow, but infrared and radio telescopes reveal a very different picture. In those wavelengths, the dust becomes transparent, allowing us to see stars, gas, and even hints of the central black hole's activity. This dusty curtain softens the intense radiation from the core, shielding our region of the galaxy. As you imagine this warm, glowing center hidden behind a dark, hazy veil, you can ease naturally into the next truth: the core may not always have been so quiet. Although the Milky Way's centre is quiet today, evidence suggests that Sagittarius A star was once far more active. Subtle reflections of X-rays in nearby gas clouds show that the black hole may have flared brightly centuries ago, briefly illuminating the core. Even more dramatic are the giant gamma-ray structures stretching above and below the galaxy, vast bubbles that seem to record an era when the centre released enormous amounts of energy. In those distant times, the heart of the Milky Way might have glowed like a quasar, one of the brightest objects in the universe. Perhaps it consumed a large cloud of gas or the remains of a small galaxy that wandered too close. Those echoes remain faint today, but they whisper of ancient turbulence. As you imagine this once brilliant core slowly dimming over millions of years, your thoughts may drift naturally toward those soft, towering shapes still floating above the galaxy. Above and below the Milky Way's disk stretched two immense lobes called the Fermi bubbles, structures so large that each spans tens of thousands of light years. They glow faintly in gamma rays, too subtle for human eyes, yet unmistakable to sensitive instruments. Their size suggests a powerful force inflated them, perhaps jets from the central black hole, or intense star formation in the core that pushed hot gas outward. Whatever their origin, the bubbles represent the lingering breath of past activity, still hanging in space like faded lanterns. Their edges ripple gently, shaped by magnetic fields and the slow movement of surrounding gas. As these bubbles float in your imagination, vast and quiet, you can drift into how astronomers study such hidden regions using radio waves that trace the swirling gas near the black hole itself. Even though dust blocks our optical view of the galactic center, radio waves penetrate the veil. Networks of radio telescopes watch the motions of gas spiraling towards Sagittarius A star, revealing streams that twist, heat and glow as they approach the event horizon. By combining telescopes across Earth into a single virtual instrument, scientists captured an image of the black hole's shadow, a dark circle surrounded by a glowing ring of hot plasma. These observations show how matter behaves under extreme gravity, providing rare glimpses into the physics of accretion. Every flicker of radio light tells a story about turbulence, temperature, and motion near the galaxy's heart. As you imagine this patient listening, this quiet mapping of invisible signals, your thoughts can drift outward to something larger, the galaxy itself slowly spinning like a vast, graceful wheel. The Milky Way is in constant motion. Stars, gas, dust, and dark matter all rotate around the center, creating a gentle, galaxy-wide swirl. The inner regions orbit faster, the outer regions slower, yet the overall structure holds together in a vast, flowing rhythm. Our solar system is just one small point riding along this rotation, completing a single orbit only once every few 100 million years. We never feel this motion, yet it shapes our place in the galaxy. The spiral arms drift around us like long traffic patterns, waves moving through a crowd rather than fixed structures. As you imagine this slow, steady turn like a wheel floating through the dark, your thoughts may drift toward the span of that journey, the immense length of what we call a galactic year. A galactic year is the time it takes the Sun to orbit the Milky Way once, roughly 225 to 250 million Earth years. In the span of a single orbit, continents drift, oceans open and close, and entire species rise and vanish. When the Sun last passed through its current place in the galaxy, dinosaurs were only just beginning to walk the Earth. All of human history occupies only a tiny fraction of one galactic year. Yet this long, looping path shapes our cosmic environment, carrying the solar system through different regions of gas, dust, and gravitational influences. As you imagine this vast timescale, slow, gentle, and steady, you can drift naturally into the thought that the Sun has only made a surprisingly small number of these orbits. Despite being 4.6 billion years old, the Sun has circled the galaxy fewer than 25 times. Each orbit is a long, quiet journey through ever-changing regions of space. Spiral arms stretch and shift, clouds drift, clusters dissolve. The Sun moves steadily along its path, carrying the Earth and the planets with it. We tend to think of the galaxy as fixed, but the Sun's slow progress tells another story, one of ongoing change and motion. As you imagine this long, looping journey, your awareness can drift toward the subtle difference between the movement of stars and the movement of the spiral arms themselves. The spiral arms of the Milky Way are not made of a fixed set of stars. They are patterns, density waves rippling through the disk. Stars move into an arm, spend some time within it, and eventually drift out again, much like cars moving through a traffic jam that remains even as the vehicles change. These waves compress gas, triggering star formation and creating the bright blue clusters that line the arms. Meanwhile, older stars continue their orbits, following their own paths. The arms persist, but the stars within them are always changing. As you imagine this gentle pattern, motion within motion, you can drift toward another subtle movement, the Sun's slow bobbing above and below the galactic plane. As the Sun orbits the center, it doesn't stay perfectly aligned with the galactic plane. Instead, it moves in a soft, wave-like pattern, rising above the plane, dipping below, then rising again. One full oscillation takes tens of millions of years. This motion is caused by the combined gravity of stars, gas, and dark matter in the disk. We feel none of it, but the movement is real, gentle, and predictable. You can imagine it like floating on a slow ocean swell, upward, downward, forward, always moving. And as you picture this quiet rhythm, your thoughts can drift towards the layered structure of the disk itself. The Milky Way's disk is not uniform. It has two main components: the thin disk, where younger stars and star-forming regions reside, and the thick disk, which contains older stars with orbits that tilt and wobble more. The thin disk holds most of the galaxy's gas and dust, arranged into bright spiral arms. The thick disk extends farther above and below the plane, forming a puffier, more diffuse structure. These layers likely formed through a mix of early mergers, turbulent gas flows, and billions of years of evolution. As you imagine these layers resting within each other, thin, thick, luminous, quiet, your thoughts can drift to the next truth. The Milky Way's appearance is not fixed, but slowly shifts over time. The Milky Way is constantly changing. Spiral arms strengthen or fade. The central bar can grow longer or shorter. The disk can warp, ripple, or relax. Interactions with satellite galaxies tug at the outer regions, stretching them into arcs or bending them like a soft sheet. Streams of gas flow inward and outward, altering where new stars form. Over billions of years, the galaxy's shape subtly evolves, like a cloud shifting in a slow breeze. Though these changes unfold far too slowly for us to notice, they shape everything we see in the night sky. And as you settle into this idea of gentle, ongoing transformation, your thoughts may drift naturally toward the unseen force that holds the galaxy together: dark matter. The Milky Way spins far too quickly for its visible stars, gas, and dust to keep it bound. Something unseen, something enormous, must be adding gravity. This invisible mass is what we call dark matter, a substance that neither emits nor reflects light, yet outweighs all the luminous matter in the galaxy many times over. Without it, the outer stars would drift into space. With it, the galaxy holds together as a single, graceful structure. Even though we cannot touch it or see it, its influence is everywhere, in the rotation of stars, in the shape of the halo, in the stability of the spiral arms. Dark matter forms a quiet scaffold around the Milky Way, a gentle gravitational cradle. And as you imagine this unseen support, you can drift toward the thought that even the shape of the galaxy depends on it, with more mass residing outside the disk than inside. When we picture the Milky Way, we imagine its glowing spiral arms and bright star-filled plane. But most of its mass is not in that luminous disk at all. It sits in a vast invisible halo extending far beyond the furthest stars, an enormous sphere made mostly of dark matter. This halo gives the galaxy its gravitational strength, shaping the orbits of stars and anchoring the spiral structure. Only a small fraction of the Milky Way is made of the shining material we can see. The rest surrounds everything like a silent cocoon. As you picture this enormous, unseen envelope, you can drift toward a deeper truth. The galaxy has not always looked as quiet as it does today. Once, long ago, its center may have burned far brighter. Although Sagittarius A star is calm now, evidence suggests a violent past. Light reflected off nearby gas clouds hints that the central black hole once flared dramatically, releasing immense energy. If true, the Milky Way may have briefly resembled a quasar, one of the brightest objects in the cosmos, its core shining so fiercely it could outshine the rest of the galaxy combined. This ancient fire has long faded, leaving only subtle echoes in the surrounding gas. Sometimes, faint X-ray flashes still appear, reminders of distant activity. Imagining that transformation from blazing quasar to quiet giant feels like watching a campfire burn down to embers. And as those old flames fade in your mind, you can drift toward the thought that even now, faint relics of that past linger in enormous structures surrounding the core. Gas clouds near the galaxy's heart still glow faintly with the memory of past outbursts. These clouds act like cosmic mirrors, reflecting X-rays that once burst from the vicinity of Sagittarius, a star. Though the black hole is quiet today, the luminous signatures it left behind linger like soft afterglow. Astronomers study these reflections to reconstruct events long gone, much like archaeologists reading inscriptions left by ancient civilizations. The light is faint but steady, whispering of a time when the center pulsed with energy. As you imagine these soft reflections, like embers catching the last faint traces of heat, you can drift naturally toward larger structures shaped by these past events, including the monumental gamma-ray bubbles that rise above the disk. Stretching tens of thousands of light-years above and below the Milky Way, the Fermi bubbles are colossal, balloon-like structures glowing quietly in gamma-ray light. Their origins remain a mystery, perhaps long-ago eruptions from the central black hole, or waves of star formation that pushed hot gas outward into the halo. Whatever their cause, the bubbles hover like ghostly pillars, enormous yet silent. Their edges shimmer faintly, shaped by cosmic rays and magnetic fields. From afar, they would make the galaxy look like a lantern with two glowing plumes. As you picture these immense forms drifting above the disk, your mind can ease into another quiet truth. Many invisible structures shape the galaxy's motion, and among them, gravitational waves ripple gently through the Milky Way. Across the universe, massive objects collide, black holes merging, neutron stars spiraling together, galaxies brushing past one another. These events create ripples in space-time called gravitational waves, which spread outward like faint vibrations in a vast cosmic sea. Some of these waves flow through the Milky Way, stretching and compressing space by unimaginably tiny amounts. We never feel them, yet sensitive instruments can detect the soft tremble. These waves carry stories of ancient collisions, far-off catastrophes, and cosmic dances we cannot see. As you imagine these ripples passing silently through our galaxy, you can drift toward the idea that the Milky Way itself is shaped not only by stars and gas, but by a complex network of magnetic fields threading through the disk. The Milky Way is woven with a subtle magnetic web, lines of force stretching through the disk, rising into the halo and curling along the spiral arms. These fields are weak compared to Earth's magnetism, but over cosmic distances they guide the motion of charged particles, shape the flow of dust, and influence star formation. Radio waves reveal these invisible structures, showing arcs, loops, and filaments that drift through the interstellar medium. The magnetic field is like a quiet tide, felt not through light, but through the movement of matter. As you imagine these gentle threads weaving through the galaxy, you can settle into the next idea that even the empty spaces between stars are filled with structure and motion. Between the stars lies not emptiness, but a thin mix of gas, dust, and plasma, what astronomers call the interstellar medium. Though delicate, it forms a restless ocean across the galaxy. Supernovae sweep through it like storms, carving out bubbles and cavities. Magnetic fields twist it into filaments. Shock waves ripple across it for hundreds of light years. Cold clouds drift through warm regions. Warm gas slides into hot bubbles. This constant movement shapes where new stars will form and how old ones will fade. As you imagine this slow, swirling sea, quiet but always shifting, you can drift towards something even more mysterious. Planets wandering alone through this medium, untethered to any star. Not all planets orbit stars. Some form normally and are later ejected from their systems. Others may form directly from collapsing gas without a star at all. These rogue planets travel through the Milky Way in darkness, cold, silent worlds lit only by faint starlight from afar. There may be billions of them drifting through the disk and halo. Though invisible to the eye, they move steadily through the galaxy's currents like stones carried by a slow river. Their journeys are long and solitary, yet they are part of the Milky Way's story, shaped by gravity like everything else. As you picture these lonely worlds drifting quietly through the dark, you can drift toward the next truth. Even the dust floating between stars carries the raw materials for life. Interstellar dust is made of tiny grains, microscopic bits of carbon, silicon, and ice drifting between the stars. Many of these grains carry complex organic molecules, simple alcohols, aromatic hydrocarbons, even the chemical precursors to sugars and amino acids. They form in the outer layers of dying stars, are pushed into space by stellar winds, and wander through the galaxy for millions of years. When clouds collapse to form new stars and planets, this dust is incorporated into them, seeding young systems with the ingredients for life. As you imagine these delicate grains floating through the dark like tiny messengers, your thoughts may soften into the idea that the galaxy is not just stars and gas. It is a place where the building blocks of life drift quietly through space. In the coldest, darkest regions of the galaxy, enormous clouds of gas and dust drift quietly through space. Within these clouds, organic molecules, carbon chains, alcohols, simple acids, form naturally as radiation and chemistry work together, at an unhurried cosmic pace. When a cloud collapses under its own gravity, becoming dense enough to ignite new stars, these molecules become part of the swirling disk that forms planets, moons, comets, and asteroids. Over time, these building blocks settle onto young worlds, carried by falling dust, icy debris, or vapor that condenses in gentle rains. And while none of this guarantees life, it means the galaxy naturally spreads the ingredients for it, like tiny seeds carried on a silent cosmic breeze. As you picture these drifting molecules finding their way into newborn systems, you can ease into the thought that stars themselves also vary in extraordinary ways, some spinning with astonishing speed. Most stars rotate at a gentle pace, but some whirl with breathtaking speed, completing a full rotation in just hours. These rapidly spinning stars flatten at their equators, bulging outward from centrifugal force, their outer layers stretched thin like a soft halo of light. Their magnetic fields twist and shimmer with activity, and their surfaces ripple with storms far more dramatic than anything on our sun. In such stars, the balance between gravity and rotation becomes delicate, almost like watching a dancer move so fast that their shape blurs. These brief-lived giants burn bright and die young, feeding new material into the galaxy when they collapse. And as you imagine their dizzying spin slowing into silence, you can drift toward the more familiar path of our own solar system, tilted gently within the broader structure of the Milky Way. When you look at the Milky Way arcing across the night sky, it rises at an angle because our solar system is tilted about 60 degrees relative to the galactic plane. It's as though we live in a small boat drifting through a larger angled current. This tilt affects how the Milky Way appears from Earth. The band of starlight shifts with the seasons, rising high during some months and dipping low during others. Yet the tilt also helps us see different parts of the galaxy at different times of year, offering views into the core in summer and into the quieter outskirts in winter. This angled perspective is part of our cosmic address, a gentle reminder that we're never perfectly aligned with the greater structures around us. And as you settle into that idea, you can drift towards the ancient remnants scattered high above the disk, stars older than the Milky Way's thin structure itself. High in the halo, astronomers have found white dwarfs, small, faint remnants of once brilliant stars that are older than the Milky Way's thin disk. These ancient cores formed when the galaxy was still young, before its elegant spiral structure emerged. Now they drift in slow, wide orbits like quiet embers left from a fire long extinguished. Their chemistry reveals an early time when heavy elements were scarce, and their motion carries clues about how the galaxy first took shape. These stars have been observing the galaxy's evolution for billions of years, passing through epochs as easily as clouds pass through seasons. As you picture these dim, ancient remnants gliding silently through the halo, you can drift toward the very outer edge of the galaxy, where the faintest stars orbit in vast sweeping paths. Far beyond the familiar spiral arms lies a realm of thinly scattered stars, so distant that they take billions of years to complete a single orbit around the galaxy. These distant wanderers drift through the halo in slow, extended loops, hundreds of thousands of light years from the center. Many arrived through ancient mergers, carried into the halo from smaller galaxies that the Milky Way consumed long ago. They are quiet, faint, and difficult to detect, yet they help define the galaxy's true size and the reach of its gravity. These stars form the soft boundary between the Milky Way and the darkness beyond. As you imagine these remote suns drifting through the outer night,
you can ease into another gentle truth. The galaxy itself is not perfectly symmetrical. Although diagrams often show the Milky Way as a neat, perfectly balanced spiral, real observations reveal a subtler, uneven shape. One side of the disk sits slightly higher than the other. Some spiral arms are longer or brighter, and the halo itself is offset from the center. These asymmetries are like quiet scars from past interactions, ripples left behind by mergers, the tug of satellite galaxies, and the pull of unseen dark matter. Instead of a perfect pinwheel, the Milky Way is a living structure, shaped by time and influence. And there is something comforting in that. Even great galaxies wear the marks of their history. As you settle into that thought, you can drift toward the delicate tools astronomers use to map this uneven structure, stars whose brightness pulses like a heartbeat. Certain stars brighten and dim with perfect regularity, expanding and contracting in a slow cosmic rhythm. These are variable stars, such as Cephids and RR Lyrae, and their pulses act like beacons. By measuring how long a star takes to cycle through its brightness changes, astronomers can calculate its true luminosity. Comparing that with how bright it appears from Earth reveals its distance with remarkable precision. Variable stars become yardsticks scattered across the galaxy, letting us trace the shape of the spiral arms, the thickness of the disk, and the structure of the halo. They are like lanterns shining from faraway hills, helping us map a landscape we can never step outside to see. And as you imagine these calm pulses drifting through the night, you can transition naturally to the spacecraft, creating the most detailed map of the Milky Way ever made. Launched by the European Space Agency, Gaia orbits the Sun alongside Earth, scanning the sky with exquisite precision. It measures the positions, motions, and brightness of over 2 billion stars, creating a three-dimensional map of the Milky Way with detail far beyond anything imagined before. This map reveals streams of stars torn from ancient galaxies, the warp in the disk, and subtle ripples from past collisions. Gaia's measurements are so precise that it can detect the small wobble of the Sun as it moves through space, or the gentle drift of distant halo stars. Each new data release reshapes our understanding, turning the galaxy from a vague blur into a detailed landscape. As you imagine this quiet satellite charting the stars, you can drift toward the broad, luminous band we see from Earth, the galactic plane. When you step outside on a dark night far from city lights, you may see a pale band of starlight stretching across the sky. This is the galactic plane, the densest layer of the Milky Way's disk. Here, stars are packed closely together, and the interstellar medium forms thick lanes of dust and gas. Through this plane, we look along the length of the disk, peering through its crowded neighborhoods of young stars, old clusters, and glowing clouds. From Earth, it appears flat and thin, but in reality, it's a vast, layered structure filled with life and movement. As you picture this glowing path arcing across the sky, you can drift toward the even brighter region near the constellation Sagittarius, home to the galaxy's busy central bulge. In the direction to Sagittarius lies the heart of the Milky Way, the most crowded and luminous region of the galaxy. Billions of stars pack into a dense sphere, overlapping their light into one radiant glow. Dust clouds obscure much of it in visible light, but in infrared and radio wavelengths, the center shines brilliantly. Stellar clusters, gas streams, and the faint pull of Sagittarius A star all converge in this bustling hub. Even from our quiet position far out in the disk, we can feel the gravity of the center shaping our orbit. And as you imagine this luminous core glowing behind veils of dust,
your thoughts can soften into the idea that from Earth, we see only a thin slice of the galaxy because we live inside it. From Earth, we can never step outside our galaxy to see its true shape. Instead, we look through its disk from within, like standing deep in a forest and trying to imagine the outline of all the trees around you. The Milky Way appears as a hazy band because we're gazing through layers of stars, dust, and distant clouds stacked across thousands of light years. This inside-out perspective makes it challenging to map the galaxy's full structure. We see the spiral arms only in hints, through star clusters, glowing nebulae, and lanes of dark dust that trace loose curves. Every view is partial, like trying to piece together a vast mural from scattered fragments. And as you picture yourself standing inside this cosmic forest, surrounded by starlight stretching in every direction, you can drift toward a gentler truth. The galaxy holds far more than human eyes can ever fully perceive. Even with our best telescopes, we glimpse only a tiny fraction of the Milky Way. Dust clouds hide enormous regions from view, absorbing visible light and leaving us with only shadows of what lies behind. Stars too faint or distant remain invisible to the eye, and entire populations of dark matter pass through space completely unseen. Yet these hidden layers shape the galaxy just as much as the luminous ones. They form the scaffolding of gravity, the currents of gas, the webs of dust, and the quiet fields where new stars are born. In truth, most of the Milky Way exists beyond our senses, reachable only through carefully tuned instruments, faint signals, and subtle motions. And as this idea settles into your thoughts, you can drift toward a more personal reflection that even within this vastness, we carry pieces of the galaxy inside us. Every atom of iron circulating through your body was created in the heart of a massive star long before the sun existed. When that ancient star reached the end of its life and collapsed into a supernova, its core fused iron in a final burst of energy. Then it shattered, sending those atoms outward at tremendous speeds, scattering them across the galaxy. Over millions of years, they mixed with gas and dust, becoming part of new clouds, new stars, and eventually the young solar system. The iron settled into planets, oceans, and living organisms, including you. In this way, the galaxy is not just above you, but within you. The same stardust that glows in distant nebulae flows quietly through your veins. And as you soften into that thought, you can drift toward the gentle reassurance that the Milky Way, enormous and ancient, continues to evolve even now. Though the Milky Way feels timeless, it is always shifting. Spiral arms stretch and drift. Gas clouds collapse into new stars. Stellar winds carve bubbles through the disk. Dark matter continues to pull in material from the outskirts. Even now, streams of stars from smaller galaxies spiral inward, weaving themselves into the halo like quiet threads. Over billions of years, the shape you know, the elegant spiral, has formed, dissolved, and reformed again. What we see today is only one chapter. The galaxy is not a finished structure, but a slow work in progress, shaped by collisions, gravity, and time. This gradual evolution unfolds so slowly that no human lifetime could detect it, yet it continues all the same. And as this idea settles, you can drift toward the even larger structures surrounding us, the quiet family of galaxies to which we belong. Our galaxy is not alone. It lives in a small gravitational community called the local group. This cluster contains more than 50 galaxies, some large like Andromeda, others tiny and faint like shadowy dwarfs drifting through the dark. All of them are linked by gravity, moving together through space in a slow cosmic dance. Some orbit one another, some fall inward, and some drift quietly on the outskirts. Over time, these galaxies may merge, reshape one another, or dissolve into streams that crisscross the group. Viewed from afar, the local group would appear as a loose gathering of glowing islands drifting along the cosmic web. And as you imagine this collection of neighbours moving gently through the dark, you can ease into the understanding that our galaxy is moving too, pulled by deeper tides of gravity. Although separated by millions of light years, the galaxies of the local group are tied together by gravity. They are not drifting apart the way most galaxies in the universe are due to cosmic expansion. Instead, they orbit a shared centre of mass, like a family of enormous islands in a quiet, dark sea. Some, like Andromeda and the Milky Way, move toward each other. Others circle more distantly, tracing long arcs that take billions of years to complete. Because of this shared gravitational bond, the local group has its own internal history, marked by mergers, exchanges, and collisions still unfolding. As you picture these slow motions across unimaginable distances, you can drift toward the structure that defines most of the Milky Way's visible beauty, its luminous, star-filled disk. To the eye, the Milky Way's disk looks like a thin ribbon, but in reality it has depth and texture. The thin disk, bright and full of gas, is where most new stars are born. Above and below it lies the thick disk, older and puffier, filled mostly with ancient stars moving on tilted paths. Together, these layers form a structure that ripples, warps, and bends. The disk is not rigid, it sways in response to gravitational nudges from the halo, satellite galaxies, and past interactions. This layered complexity is part of what makes the Milky Way a living environment, rather than a static picture. And as this image settles in your mind, you can drift into the quieter, more mysterious realm that surrounds all of it. Encasing the Milky Way is an enormous halo of dark matter, an invisible sphere extending far beyond the spiral arms. Though we cannot see it, its mass outweighs all the stars and gas in the galaxy many times over. The halo bends the motion of stars, stabilizes the disk, and anchors the galaxy's rotation. Without it, the Milky Way would fly apart. The dark matter halo also holds ancient star clusters, drifting streams, and the faint traces of galaxies long ago absorbed. It is the galaxy's hidden foundation, steady and silent. As you imagine this unseen sphere enveloping our entire cosmic home, you can let your thoughts drift toward the way the galaxy gently moves through the larger universe. Although it feels like we are standing perfectly still, the entire Milky Way is hurtling through space at hundreds of kilometers per second. We orbit the local group's center of mass, drift through the cosmic web, and move toward a vast region of space called the Great Attractor. These motions are so smooth and constant that we never feel them, yet they carry us across millions of light years over cosmic time. Every star, every cluster, every cloud in the galaxy participates in this grand movement. And as you imagine the whole Milky Way gliding through the dark, you can drift toward a final calming truth. Despite all this motion, your small corner of the galaxy is peacefully stable. In the grand structure of the Milky Way, our solar system resides in a calm region called the Orion Spur, neither too close to the bustling galactic center nor too far into the sparse outskirts. Here, supernovae are less common, gravitational disturbances are gentler, and the density of stars is just right for life to evolve in relative peace. This quiet corner has allowed Earth to orbit steadily for billions of years, giving life the time and stability it needed to grow and change. As you settle into this gentle truth,
that you live in a small, safe harbour of a vast and ancient galaxy. You can feel your thoughts soften, your breathing slow, and the night around you grow a little quieter.